In today's episode, we are going to look at temperature and shear stress. Temperature and shear stress. And we will talk about the effect of temperature on bars and how shear is caused in members. We know that it is not only external forces that will cause strain and stress in members. Yes, temperature is also a factor that can cause strain and stress in members. So let's deduce how this came about. Now, let's consider a bar. We have a bar of length AB, and initially this is at a temperature, let's say theta. Now, the bar is subjected to an increase in temperature. We try to increase the temperature from theta to a temperature, let's say change in theta. So, initially the T1 is theta, and to another temperature 2, which is change in theta. What we are going to observe is that initially the bar had this length from A to B. That was the initial length of the bar and the original length of the bar when the temperature was what? T4 or at theta. Now, we cause an increase in temperature, and this bar is going to now elongate or contract when there's a change in what? Temperature. As we increase the temperature, the bar will try to expand or elongate through this length, and this will be the deflection as a result of the change in the temperature. Let's say T1 was around 20 degrees Celsius and T2 now is 40 degrees Celsius. The temperature change is going to be 40 minus 20, giving me 20. So a temperature change of 20 degrees Celsius is going to cause this bar to elongate by an amount, this deflection. So we are going to get a new length for the bar. And from analysis, the strain, we know the strain is the deformation produced. That's the elongation that what we produce in the bar. And the thermal strain, here we are dealing with temperature. So the strain, thermal strain, we know that strain is represented this way, and it is thermal, temperature strain. It is giving us that to change in what? Temperature, T. This is the strain, where A is what we call coefficient coefficient of thermal expansivity or expansion, thermal expansion, yeah, or the coefficient of linear expansivity. It has the units 1 on Kelvin or 1 on degrees Celsius. But remember, when you find a temperature change, the unit is now not going to be what affected, because if this is 40 degrees Celsius and I find the difference between them, I'm going to get 20 degrees Celsius. The same way, if I convert them to Kelvin and find the difference, it is still going to give me 20, because to send this into Kelvin, we're going to add 273, 273. They're going to cancel out, and the difference is still 20. So the unit can be per Kelvin or per degree Celsius. So in temperature stresses, the strain, the thermal strain, is giving us the coefficient of thermal expansivity times the change in temperature. And we are going to get the strain produced. And the corresponding stress, where the strain, mostly stress is induced. The corresponding stress, but we will talk more about how the stresses are engaged, because not all members under temperature action will be having stress in them. For example, if the bar is free to expand, if there's gap for expansion, there will be no stress inside the bar, so stress is going to be zero. Take note, a bar which is allowed to expand freely will have no stress. So here we have the stress. From Hooke's law, we know that stress is E, and the strain. But now we know the strain as coefficient of expansivity times change in temperature, meaning which implies that our stress, thermal stress, of course, is change in temperature and the coefficient of expansivity. This is the induced thermal stress. But let's take note once again. Anytime a bar is allowed to expand without restricted, it has a strain, all right, but the stress induced in the bar is always zero because it is allowed to expand under the action of what? Temperature. Let's look at this bar. Consider this prismatic bar of length. We have the length to be what? L, and is subjected to a temperature difference, that's change in temperature, and we are going to have the elongation what? Produce. And so we know that, let's look at this formula. We know that from our previous slide, the thermal strain is giving us this times change in what? Temperature. I'll use change in T as my temperature change. This is the strain. What about the deflection? How do we get the deflection produced? This is the small deflection produced when the temperature was what? Increased. It expanded by what amount? That's the deflection. We know that deflection or strain is equal to deflection or change in length over the original length. So we can say that the deflection is the strain, the thermal strain times the original length. Therefore, our deflection by temperature is going to give me, we are going to replace by this, the length times this change in temperature. And we are going to have the expression for the deflection produced as a result of temperature change. Alpha L change in temperature. This is the elongation or the deflection produced. What about the final length? So if I'm to find the final length, which is from this side to the point it completed its elongation, this total distance is going to be my final length. So we can say that the final length is going to be the initial L plus the small deflection, and we know that the small deflection is the length alpha and change in temperature, which is going to be L alpha change in temperature. So the final length is going to be L out 1 plus alpha change in temperature. So this is the expression for the final length when a bar is allowed to what? Elongate under the action of temperature. That'll be the final length. So we have these formulas there. The strain, thermal strain, is alpha change in temperature as equation 1. We know that when the motion or the elongation is restricted, we are going to have a stress, which is the temperature. This is equation 2. But remember, anytime the bar is allowed to elongate without restriction, the stress induced is 0. And we have our elongation, thermal elongation, to be the length alpha change in temperature as our equation 3. The final length is going to be the length 1 plus a change in alpha change in temperature. So we should keep in mind these 4 equations under temperature and shear stress, especially temperature stresses. This is for unrestrained bars. There's no restraint. The bar is allowed to what? Expand on its own. When the bar is restrained, it has its own approaches, how we are going to deal with the bar in terms of the stresses and the strain. But if the bar is allowed to move or is allowed to expand freely, then the stress induced in the bar is 0. Let's take an example. A steel bar of length 200 millimeters is at a temperature of 100 or 10 degrees Celsius. This is degrees Celsius. If the material property are E that and the thermal expansivity is 12 to the power negative 6 per Kelvin, we have to find the thermal strain and the new length. So let's write down our parameters. We have the length, initial length L, 200 millimeters. That will be 0.2 meters. We have our initial temperature T1, and that's giving me 10 degrees Celsius. I have my E, Young modulus, which is 210 gigapascal, and expansivity is giving us 12 times 10 negative 6. Don't say this is per Kelvin and this is per or degrees Celsius. Anytime you find the difference or the change in temperature, you are going to arrive at a constant answer, whether it is in Kelvin or degrees Celsius. What about T2? It was heated up to. Find the new length of the bar when it is heated to 23 degrees Celsius. So our T2 now is what? 23 degrees Celsius. So can we find our change in temperature now? Yes. Our change in T is going to be the T2 minus T1. So change in T will be 23 degrees Celsius minus 10 degrees Celsius. And I'm going to get 13 degrees Celsius. So back to my question. The thermal strain. And I know that thermal strain is giving us what? The alpha change in temperature. So I have all of them. The alpha is a constant. Every material has its expansivity, so it is a constant value. So let's look at this. So thermal expansivity or the thermal strain is, we have 12 to the power negative 6 multiplied by the change in temperature, which is what? 13. And I'm getting the strain, thermal strain, to be 1.56 times 10 to the power negative 4. So this is the thermal strain. The new length of the bar when it is heated to 23 degrees Celsius. So we are going to find the new length. After the bar was heated, there was an elongation. So we need to find the new length or the final length. And we know that the final length, which is final length LF or the new length, is going to give us the length into bracket 1 plus change in temperature. So what is the length? You can use it in millimeters or in meters. So 0.2 meters, 1. The expansivity, which is negative 6, and the change in temperature, 13. So my final length is going to be 0.2000312 meters, which is approximately 200.0312 millimeters. So this will be the final length. So in case the question asks for the deflection or the change in length, that's going to be the final length minus the initial length. And we are going to get, we can use the millimeters, 200.0312 minus 200. Meaning the change in length was 0.0312 millimeters. So under the action of this temperature change, which is 13 degrees Celsius, the bar was able to elongate by 0.013 millimeters. That's quite interesting. Example 2. Let's look at how this example also goes. It's interesting. A 150 millimeter diameter steam pipe is laid in a trench at a temperature of 13 degrees Celsius. When steam passes through the pipe, its temperature rises to 120 degrees Celsius. Now, what is the increase in diameter or the change in diameter of the pipe if the pipe is free to expand in all directions? Now, what is the axial stress in the pipe if the trench restrains the pipe so that it lengthens only 1/3 as much as it would if it could expand freely? Let's take note. The pipe is made of steel with modulus of elasticity 200 and coefficient of thermal expansion that. So I can get down my parameters and start working with them. So from the question, what do I have? I was given the diameter, which is D, to be 150 millimeters, and that will be what? 0.15 in what? Meters, but I can work in millimeters. My T1, the initial temperature, was given as 13 degrees Celsius. Was 13 degrees Celsius. I also have my T2. As steam, we know steam is what? A heated vapor. It's highly heated. When steam passes through the pipe, this pipe was used to deliver steam from one point to another. So the steam heated the pipe to another temperature, 120, which is 120 degrees Celsius. So I can find my change in temperature now to be 120 minus 13 degrees Celsius, and my change in temperature now will give me 107 degrees Celsius. I have my E to be 200 gigapascal. I have my expansivity to be 12 times 10 per Celsius or per degree Celsius. So, what is the increase in diameter? Increase in diameter. We know that for bars or for materials under thermal action or the influence of what temperature, the change in length or the deflection in length is giving us what? The length A and change in what? Temperature. So this time it is not increasing in length but rather increasing in diameter, which is the same thing. So we can say change in diameter is going to be the diameter alpha change in what? Temperature. And we know the diameter to be 150 times the alpha, which is 12 to the power negative 6. The change in temperature, which is 107. So at the end, we are going to have change in diameter to be 0.1926 millimeters. That's quite simple. Change in diameter, change in length, or the deflection produced. We have diameter, expansivity, and change in temperature. That's for the I part. II. What is the axial stress? We are looking for stress now in the pipe. If the trench restrain the pipe so that it lengthens only 1/3 as much as it would if it could expand freely. I initially told you, let's consider this bar. If this bar is under the influence of what temperature and it is allowed to expand freely without any restriction, there will be no stress. So if the question said it was expanded or it expanded freely, meaning stress induced is 0. But if partially restricted or fully restricted, meaning stress is going to be induced in the system. So looking at the question, they're trying to restrain the pipe instead of the pipe to elongate or expand on its own. They're trying to now restrain the pipe from what? Expanding. So its length is only 1/3, meaning there was an amount which wasn't what? Free to expand. And that amount is going to cause a stress in the pipe. So we have to find that stress. But what do we know? We know that stress, that's what thermal stress is E, and the thermal what? Strain. We know this way. And we also know that the thermal stress, this strain, we know from initial that strain is change in length on what? Length. But this we are using diameter, which is change in diameter on what? Diameter. So I can replace this by change in diameter, which is the thermal strain over the diameter times the Young modulus. But looking at the question, it says it lengthens only 1/3. So instead of the bar to lengthen fully, which is a whole number 1, it was able to lengthen only 1/3 of it, meaning there was an amount which was restrained, and that amount which was restrained is going to cause an equal what? Strength or equal strain or stress, an equal stress in the bar. So let's find the amount which wasn't able to expand freely. So 1/3 was able to expand. Therefore, we can say it lengthens only 1/3. So there was only 1/3 change in what? Diameter. Then what was the amount that wasn't able to lengthen? Therefore, the change in diameter that wasn't able to lengthen is going to be now the change in diameter minus 1/3 of it. Yes, this is the whole change in diameter that was supposed to expand freely, but 1/3 of it was able to expand. Meaning if I subtract 1/3 of the expansion or the lengthening from the original change in diameter, I'm going to get the left over what? Diameter, or the diameter which was what? Restrained. So what was the diameter? Now I have the change in what? In diameter, which is 0.1926 minus 1/3 that was what? Able to expand. Meaning the amount that was restrained was 0.1284. I'm working in millimeters. So this amount of what? The diameter was restrained from lengthening. So it was pushed back. And this one is going to cause a stress in the pipe. Therefore, we can say that the thermal stress is equal to, now the change in D is going to be the D that was restrained, which is 0.1284 on D, and the D is, this is in millimeters, the D is 150 multiplying the E, which is 200. Since I'm working in millimeters, this is not going to be in times 10 raised to the power what? 9, because remember, we are going to say that 10 raised to the power 6 in Newton meter square is equal to 1 Newton per millimeter square. So meaning I'm going to be left with 10 raised to the power 3, which is going to give me 171.2 megapascal. Pascal. So this is the induced thermal stress as a result of the restrained diameter. So if the question has said it was not able to lengthen, then we could have taken the entire change in D, but the 1/3 of it was able to lengthen, meaning it is out, leaving the rest behind. So those left behind are going to be used to calculate for our thermal stress. It's quite simple. So let's look at statically indeterminate bars. The bar is restricted, no movement. You are not going anywhere. It is restricted at B and at A. And remember, anytime a bar is given to you to work on it, we are going to remove it from its support. And this is the free body diagram. We have the original length. There is going to be a reaction acting this way and a reaction acting. So the reaction at A is RA and the reaction at B is what? RB. There was a temperature change in this bar. There's a temperature change in this bar. And this bar, if the temperature change was positive or high, this bar is to what? Is to elongate. But since it is fixed, the elongation is not going to what happen. It's not going to be possible because now it is fixed. So it is going to induce what? Stress inside the member. It's going to induce stress inside the member. So if the change in temperature is negative, it is going to what? Contract. And since it is fixed, the contraction is also not going to be possible because this support is not going to detach or is not going to allow the bar to what? Either move up or what? Come down. It is holding it what? Fixed. But in reality, there should be a deflection, either contraction or elongation, but the bar has a fixed end, which is what? Preventing all those stuffs. So we are going to calculate for the deflection that was supposed to happen and it was prevented, and the stress that prevention is going to cause in the member. It's quite interesting. So this is the deflection that was supposed to what? Happen. But as a result of the fixed end, the bar now refused to either contract or elongate, causing a huge stress inside the member. So let's look at an example. It's interesting. This bar is fixed at both ends, aluminium and steel, but it is fixed at both ends. So let's look at what happens inside this bar. This example is quite interesting. Pay attention and get the understanding. Looking at this bar, it is fixed at a point and there is an action of what? A force acting. Look at, there's a 200 kilonewton force what? Acting inside the bar. And yes, we know that when there's a temperature change, this bar, if these ends are freed or are removed, it is going to elongate or contract due to temperature change. But now it is fixed, so it is not going to be what? Possible. Meaning there's going to be what? Stress, and there's going to be what? A possible strain. So let's take a question. A composite bar, a bar made of what? Aluminium bar and what? Steel, is firmly held between two unyielding supports. Unyielding, not moving, they are fixed, as shown in the figure below. An axial load, 200 kilonewton, is applied at B. This is the 200 kilonewton. Find the stress in each material when the temperature is 97 degrees Celsius. You should take E to be E of A, which is the modulus of aluminum to be 70, for the steel to be 210, the expansivity of aluminum is 24, and that of steel is what? 12. So all the parameters are there. First, since there's an influence of what? A force inside the member, we are going to detach it from its support. It's going to get what? A reaction at the end. So if I'm to detach that bar, I'm going to get it in this form. This is a free body diagram. That's my diagram. Now, this bar is what? This is the steel. This is the force acting in it, which is 200 kilonewtons. This section from A to B to C. And looking at the support, looking at the temperature change, it was what? It is going to be positive. Initially, it was 70, and its final is going to be what? 97. So the difference is going to give you what? A positive answer, meaning the bar in actual sense is to what? Elongate. But this bar, the rigid supports are pushing the elongation back this way. So this fixed end is pushing it back this way. The reaction R at C, and at A to it is pushing it back that way. That's R at what? A. When we were doing axial loaded bars, I would have taken my reaction to be opposite to this, but in this scenario, it is different because the bars are what? Now trying to compress the bar. The fixed ends are now trying to compress the bar from what? Elongating. That's quite interesting. So we can write our first equation from this one. So I can say that the reaction at A plus the 200 kilonewton is equal to the reaction at C. Yes, that's true. And inside this bar, there are two things causing both the stress and the strain. The action of what? Temperature, and the action of what? Forces. Remember, forces are going to cause the respective forces are going to cause strain and stress, as well as the temperature increase is also going to cause a strain and what? A stress. So the two of them are going to work. And what we are going to say from our main focus is that the entire strain or the entire deflection from A to C, the entire deflection, pay attention, the entire deflection from A to C is equal to the deflection produced by the temperature minus the deflection produced by the force. Are we good? So when we take the deflection by the force and the deflection by the temperature, we are going to get the entire deflection. This is what we have. So we are going to consider, first let's consider the temperature effect. So this is our equation 1. Let's consider temperature or thermal effects. We are looking at what the temperature is going to cause. The thermal effect, can we say that the total thermal effect is going to be the thermal effect at AB plus the thermal effect at what? BC. Yeah, it makes sense. Now the entire elongation that will be produced by the temperature change, since they are of different materials, it is the one of A and the one of what? B, that way. And how do we find the elongation produced by temperature? We know that it is the length of AB and what? The alpha of AB times what? The change in what? Temperature. The same thing at BC, the length of BC, alpha of BC, and change in what? Temperature. So we can bring back our value. So the total deflection by temperature is going, what is the length of AB from the question? 100 millimeter, which is 0.1 meters, times A the expansion constant of the alpha or the AB is aluminium A, 24. So we're going to get 24 to the power negative 6. What is the temperature change? The temperature change is going to be 97 minus 47, which is going to give us what? 50. So 50. That's the temperature change. That's for the steel. And the BC, that's the steel. The length is 150 millimeters, which is 0.15. What is the A? The alpha, the constant of steel, which is 210. The A of alpha, which is 224 to the power negative 6. So the steel is 12 to the power negative 6. Change in temperature is 50 as well. So punching all this, the entire temperature change is going to give me 2.1 times 10 raised to the power negative 4 meters. So only the temperature is going to deflect this entire bar by this amount. So suppose the question asked or there was only temperature effect on this bar. This will now be the corresponding what? Deflection. There wouldn't be any effect of force if the question hadn't bring this 200 kilonewton force. This will just be the what? The deflection, and we can play with it to get the stress. But now temperature is working and there's force also what? Working. So let's consider the force effects. So considering, that's quite interesting. Considering the forces. So the entire deflection by the forces P. So the entire deflection by the forces is going to be the deflection in what? AB plus the deflection in BC. And we know the formula for deflection to be what? The force times the length on the area times the Young modulus. And so the entire deflection by the force. Let's find the deflection in AB. So in AB, what force is acting in AB? When I section AB, I'm going to get this force RA. That force RA acting inside what? That. So I'm having RA as the force acting. Are we good? That will be the force acting inside by AB. So RA, the force times the length. What is the length of it? The length of AB is still 0.1. So we have 0.1 over the area. Now we have the area to be 1000 millimeter per square. 1000 millimeter square. So we can change it back to what? Meter square. By multiplying by 10 raised to the power 6. That is going to give us, so we have 1000 multiplying 10 to the power 6. And we have the E, the Young modulus of the aluminium to the 70, which is 70 times 10 raised to the power 9, plus the same thing to the bar BC. In bar BC, the force acting will be what? RC. It's also a compressive force, so we are going to get RC multiplying what is the length 0.15, the area 1500, so also multiplying, we are changing to meters, which is 1500 to the power 6 times the E of 210 to the power 9. Okay, so can we say that the final answer for the forces, change in P is going to give me 1 point. I'm leaving my answer in terms of the reaction RA and what? RC. So change in P is going to be 1.4286 to the power -9. Punch all the values here and leave it in terms of RA. RA plus this 4.7619 to the power -10 RC. I have that. Okay, so what we know is that an assumption was made that the change or the thermal change is also equal to the change produced by what? The force. So from this, can we say that we know change in T already to be that? So I can equate it to that. So 2.1 to the power -4 is equal to the entire of that, which is 1.4286 to the power -9 RA plus 4.7619 to the power -10 RC. We have another equation. So this would be what? Equation 3. We have in terms of RA and what? RC. We can find the reactions from equation 1. We can bring back RC into equation 3 to find for what? RA. And when you bring equation 1 back, this is what you are going to get. So I will still have my 2.1 to the power -4 to 1.4286 -9 RA plus 4.7619 to the power -10. In place of RC, I'll put the whole of this RA plus 200 to the power what? +3, which will be RA plus 200 to the power +3. And making RA the subject from this, we are going to get RA, the reaction at A, to be 60.248 kilonewton. That's interesting. So let's look at the RC. So RC will be from equation 1. I have RA, so my RC is now going to be this 60.248 plus 200 kilonewton. They are all in kilonewton. So RC is going to be 260.248 kilonewtons. So we have our reactions, which is the same force acting in the member A and the member what? B. So can we use that to find the stress? Yeah, we know stress is force on area. So stress, which is force on area, meaning our stress in A. Let's calculate this. Stress in A. What's the force in A? In A, the force acting is RA. And we know that RA is what? 60. But remember, RA is what? A compressive force, so we can negate it. To be -60.248 on the area. The area of what? A, which is 1000 millimeters square. We can convert it to meter because we are dealing with meter. So 1000 times 10 to the power, when you are converting, we are going to divide to 10 raised to the power what? -6. So remember here, they are all -6. And my stress in what? A, the aluminium, is going to be -60.249. The same thing, the stress in B, which is for the steel, remember, it's also the force RC. When you section the B, it is the reaction force RC. It's also a compressive force. We can negate it to be -260.249 over the area. The area is 1,500 millimeters square. So in meters, that would be 1.5 times 10 raised to the power negative 3. You should know how to convert from millimeter to meter. For that one, you can play with that. So later, I'm going to get my stress in B to be negative 173.499 megapascal. This one is also in what? Megapascal. So this will be the induced stresses inside the bar as a result of what? The force and the temperature effects. You can pause or go back and get it well.